Perfect. So, a little bit about myself. My name is Christelle Harper, not member Regeneration Canada, but I am on our Zoom account for work. So, I am the Manitoba manager here for Regeneration Canada, and I've been here since July of 2025. I am located in the very southwest corner of Manitoba, about an hour from the Saskatchewan border and an hour from the US border in Treaty 2 territory. And I do have a family farm. We use regenerative practices, mainly having beef as well as a U-pick pumpkin patch, and then also a direct-to-consumer sale part of our farm. And I'm also joined by my wonderful colleagues from Regeneration Canada, Juliette, Sarah, and Digit, and Rosina will be hopefully coming in later on in the webinar as well. So I'm just going to run a little poll here. So this is what best describes your profession. So perfect. We're getting in some answers. This is very weird to be running a webinar where I can't see anyone. So I'll leave it on for a little bit longer. Okay, we got most of the participants. 17 out of 21 participated. So here is Uh, so we have about 41% are producers, 6% researchers, and then about a quarter each is advisors or others. Perfect. Let me head over. Okay, Martin, you can just see the agenda now, right? Okay, perfect. Thank you.
Yep.
So a little bit on what we're going to be covering today. I will give an overview quickly on what Regeneration Canada is, and then we're going to hear from Martin, and then we'll have the question period at the end. So if you do have questions, just pop it in that Q&A as they come up for you. Don't worry about holding on until the very end. Um, if you're like myself, that I forget stuff, so I'll type it in the chat, and we'll get to it as in the question period. So, Regeneration Canada is a not-for-profit organization dedicated to enabling the adoption of regenerative agriculture by facilitating knowledge exchange, building networks, raising awareness, and um, co-developing practical transition pathways with farmer, ranchers, and stakeholders in the industry. And I really do love this quote from our president. Beginning by building regional hubs, our goal is to support farmers in understanding the opportunities and barriers to regenerative transition in each region and sector. Through strategic partnerships, we can then work to leverage the opportunities and break down the barriers. And I truly think that is what regeneration really holds true um, to what the organization is, but as well as what the employees really value. So here is a few resources that we do have. The farm map has about 175 farms listed across Canada that are using regenerative farm principles. It's a place not only for consumers to connect with local farms for your products, but also a place that producers can connect with other like-minded producers around their area that share similar contexts. We also then have our media library, which has different sources of media, including videos, podcasts, and webinars. It is a great way to send yourself down a rabbit hole of regenerative agriculture as well. And then while you're there, head over to our toolbox for regeneration. It is our newest addition to our website. And here you'll find a ton of resources, research, and tools that's organized by topic. So if you head to our website, you'll find all of those. In the post-webinar email that we'll send out, we'll put all the links in there as well, just to make things really easy and accessible. Regeneration Canada also has two programs just to highlight more specifically about our dairy programs, one in Manitoba and one in Quebec. In the Manitoba one, the focus is determining the environmental and economic impacts of specific regenerative agriculture practices that the farms are running, while building a peer-to-peer community of dairy farmers using regenerative principles. And the Quebec dairy program's focus is to explore and optimize regenerative practices in a supportive space for dairy producers to express needs, sharing experiences, and filling information gaps. So now we have Martin. He has been a researcher in soil biochemistry and nutrients at Agriculture and Agri-Foods Canada, AAFC, since 1997. His work focuses on improving agriculture practices to enhance the resilience of crop livestock production systems and the sustainability of the agroecosystems. In particular, he participates in AAFC's Living Laboratories. And I will stop sharing my screen now, Martin, and you can share yours. But we are really excited. Martin did give this a presentation very similar to this in French a while ago, and he brought up to give it to English in English, and we jumped at the opportunity. So take it away, Martin.
Well, thank you very much, Christelle. And first, I would like to thank the Regeneration Canada members for the invitation to give that presentation this morning. So I'm glad to be with all of you this morning, and you should see now, I think, my screen, right, Christelle? Yeah, okay. So we are going to talk for the next hour or so about soil health and most specifically about the different concepts within the soil health that helps us understanding what really drives the soil fertility and crop resilience. Well, let's start first with looking into more details what I mean when I say soil health. This is my own interpretation of what's it's all about. To me, it's supported by three different pillars: soil organic matter, biological activity, and structure. And as you can see, these pillars are overlapping, and this is in the overlapping areas that we can see that soil, I would say, ecosystem services appear. So this is through the interactions between two or more of the three pillars. And what's really important is that the area where the three pillars overlap is really the place where the concepts of soil health, soil fertility, and crop resilience can exist. So that means that including practices for a balanced improvement of the three pillars is required to obtain healthy soils and increase productivity and resilience. And that also means that neglecting only one of the three pillars will reduce the actual benefits of your efforts to boost crop productivity. And soil health is a dynamic process, so that means that we have to continuously support it through regular input of fresh organic matter. Organic matter is kind of the fuel of the soil health, and regular inputs are required to sustain soil health over time because these inputs represent the main food source for everything that's living in the soil. And we'll see later on that the biological activity resulting from organic matter inputs has a major impact on structuring of the soil, so the 3D organization of soil particles altogether. And the interaction between structure and soil organic matter gives, on one hand, protection to soil organic matter, but also is very important to have good air and water circulation throughout the soil profile. And all organic residues can help, in terms of forming soil organic matter or supporting soil health, but the efficiency is not, varies depending on the different source type. So I've separated all our possible organic waste or residues that can be put on the soil in three different classes. The first source is mature crop residues. So we think about corn stovers, wheat straw when we harvest at harvest time. And now we know that about 6 to 14% of the initial biomass that's left on the soil after harvest is going to form organic matter in the soil. So that means that, say, for 1 ton of biomass, you will end up with 60 to 140 kilos of organic matter in the soil. The second class of residues is about animal manure and cover crops, but I mean more specifically the above ground parts of cover crops. For these types of residues, 12 to 23% of the initial biomass will form soil organic matter. So you can see that as compared to major crop residues, it's about twice as efficient as mature crop residues. And the third source are roots. And you can see there that the efficiency, again, doubles as compared to animal manure and above ground crop residues, up to 45% of the root biomass that eventually converts to soil organic matter. So really, roots are the summum in terms of organic matter input. So that brings, a different perspective as compared to what we used to teach to people about the old, say, the old humus formation theory that was saying that, mature crop residues are decomposed by soil microorganisms, but and that's the portion, say, lignin, the portion that is left behind because it's too complex to decompose, that forms stable organic matter. But now we know that this root ends up mainly as CO2 that's released to the atmosphere and forms just a little bit of soil organic matter in the end of the process. As compared to that, we now know that, the more biodegradable residues, such as animal manure, cover crops, and roots, are a very good food source to soil microorganisms that can convert these initial sources into microbial corpses and other molecules that will end up in a greater proportion as stable organic matter with less CO2 that's directly released to the atmosphere. So, and now we know that really soil microbes are very important because they really not just digest the say biodegradable portion of plant materials, but they really convert initial plant materials to microbial materials that really form the stable organic matter in the soil. So that's the reason why we now know that microbial activity in the soil is very important to form stable organic matter. Now let's see about the relationship between this organic matter, biological activity in soil structure in relationship to soil structure. So when we really want to learn more about the state of the soil structure, we have no choice but to dig a look. We really have to see what happens. And what we hope to find is a good soil aggregation. We'll see more about that in the next slide. So how soil aggregates is really the way a soil will be, you know, uh, will be able to absorb the rain that's coming down. And of course, what we hope not to find is, compacted soil layers and so on. So, because in this case, water and air circulation are really problematic. So, really, in terms of soil health, when we think more specifically about soil structure, the target really that we're looking for is an equilibrium between infiltration of rainwater and drainage of excess water. And that's the same as saying an equilibrium between good water reserve and good air circulation. And there are two different things that we are really looking for. The first one is about the topsoil. So, say the top 6 to 8 inches or 20 centimeters. So, what we're looking for is macro aggregation. And by macro aggregates, I'm meaning aggregates that are, larger than a quarter of a millimeter in size. So we want to increase the size of aggregates as much as possible. And here, the key players, we'll see it in more details later on, are fungi and fine roots. And these are pictures to show how fungi and fine roots act, as to form and stabilize macro aggregates. So here on the left-hand side, the photo shows a dead root that's decaying and that's colonized by a fungi that's decomposing it. So the white threads everywhere are fungal hyphae. And you can see that there are soil clods, so soil macro aggregates that are imprisoned within the hyphal web. And the same physical action appears with fine plant roots, but at a larger scale, say, of a few millimeters to form and stabilize aggregates that are enmeshed in the fine root structure. Okay, now if we schematize a little bit more what it's all about aggregate formation, say that you have a microbial colony that's surrounded, you see in red, there are mineral particles and also micro aggregates that are cemented with, say, calcium and magnesium oxides, iron oxides, and so on, surrounding the microbial colony, and you add fresh organic matter. So you make an input, say with animal manure or whatever. It will start stimulating the microbial colony that will secrete a mucus that is rich in sugars and proteins. So the main objective of that mucus is to protect the colony against desiccation, mainly, but it's also very sticky because of the presence of the sugars. So it will just, cement all the mineral particles and micro aggregates surrounding the colony into a macro aggregate. Okay, so this is what we see on the right-hand side on the picture, macro aggregate. And, in the process, there are also fungal hyphae and fine roots that will just grow within, but also around the macro aggregates, making them, more stable and resistant to wind or water erosion. These are other pictures showing, how macro aggregation can happen. So on the left-hand side, we have wheat straw that we cut and buried in the soil for 3 months, and 3 months later we removed them and shook them very hardly. But you can see that there was still soil sticking on the wheat straw surface. And a closer look in the microscopy here show we can see the soil particles, at the wheat straw surface, but we more especially see the fungal hyphae that are imprisoning the soil at the wheat straw surface, so that these fungi are decomposing the wheat straw, but they also really are the organisms responsible for that soil sticking to the wheat straw surface. And well, a long time ago, during my PhD studies, I've demonstrated that there was a direct relationship between fungal biomass in the soil and the average size or mean diameter of aggregates. So the higher the fungal biomass, the greater the diameter of aggregates. But more specifically, I also showed that the greater fungal biomass were essentially found under perennial crops, whereas we do have a certain relationship for annual crops, but the fungal biomass in general are much lower than under perennial crops. So covering the soil with living plants seems to be really the best way to obtain the maximum fungal biomass possible. And fungi are really our allies, and we have to take care of them. In general, whatever it is, a decomposer or mycorrhizae, they will stabilize soil aggregates. They will produce components that are prone to form stable organic matter, and they also increase nutrient cycling and uptake and water accessibility to plants. But they don't like soil tillage. So because tillage break down their hyphae, and so the idea is really as much as possible to reduce tillage intensity. So by intensity, I'm meaning energy, so the type of equipment, and the frequency. So to reduce the number of times we till the soil, and also it's important to reduce tillage depth, because we'll see further on that depth, fungi and roots are also well able to make soil well structured. But fungi, they also like roots very much. There is 10 up to 20 times more fungi present in the rhizosphere, so the very thin layer of soil around the roots than in the bulk soil, because fungi, they used to feed at root exudates and also at dead roots. Maybe just a parenthesis here about sandy soils. They represent a greater challenge than the heavier soils, because clays are really required to form stable macro aggregates, so very fine mineral particles. There's not enough clay in sandy soil, so the organic matter is not well protected, say, as in clay soils. So soil organic matter is therefore more easily degraded and harder to accumulate in sandy soils. And it gets even more complicated with climate change, because as the temperature warms up, the soil organic matter decomposes more rapidly. So the morality here is that we have to use a bundle of beneficial practices to protect and accumulate organic matter content, in particular in the sandy soils. Now, we've talked a lot about topsoil macro aggregation. There is a second point that we are looking for in terms of soil structure, but in subsoil, it's different. It's about porosity, and more specifically, macro porosity, that helps air and water circulation and root growth of depth. And here, the key players are roots, again, and also earthworms. Some insects, bearing insects, can also, create macropores, but roots and earthworms are really the main players here. And this is, and the following photographs will show you how it works. So biopores are really a very critical set of deep soil structures, say, and more specifically biopores that are formed by the action of living organisms. They're very important at depth because they can persist for several years and probably over a decade in time, and they facilitate root development at depth and therefore water acquisition. So the following pictures that I'm going to show you are from a long-term experiment that I've set with my colleague Marie-Noëlle Thivierge in 2016, where we established a grass alfalfa prairie. And after, at the end of the 5th year after establishment, we had installed, underground cameras in clear tubing, so we could get back, from time to time at the exact same place and see what happens over time in the soil. So here is a picture at 7 centimeters, so about a little bit more than 2 feet deep. And after 5 years after the establishment of the grass alfalfa prairie, we could see at that depth, alfalfa roots that were passing along the clear tube here. So in fall 2020, we terminated the prairie and then went back the following the next year with planting corn. So we took a picture in June, so a few weeks after planting corn in our region, and could see at the exact same place the hole that was left by the alfalfa root. It has completely decomposed, and so the biopore was still there. At the end of that growing season, in August, we could see that the corn roots were passing by the exact same path as the biopore. So they were growing directly within the biopore. Next year, we planted soybean. And so at the beginning of the growing season, a few weeks after planting soybean, we could still see the biopore, but the corn had decomposed completely. So the biopore was left empty there. And at the end of growing season, we could see that the soybean was passing by the exact same path as in the previous years. So the biopore was, over the years, was really an important passage for deep root development. And that deep root development, is very important. Well, in general, the majority of plant roots below 40 centimeter deep grow in cracks and biopores, and deep roots are key to sustain water uptake, and so they increase crop resilience in drought periods. And that's another example here of how soil structure determines how, plants can develop. And this is a picture of soybean that was grown on the 70-year-old experiment that I've set in 2009, a wheat, corn, soybean rotation, where we compare fall moldboard plowing versus minimum till, which is occasional harrowing, say maybe once every 5 years. And all these plots have the same fertilization. So last summer in mid-July, I decided to go and see how the plants were developing after 17 years of these soil tillage approaches. So after 17 years, where moldboard plowing was doing every fall, we had a bad structure, whereas in the minimum till plots, we had a very good soil structure, and you can easily see the difference in plant development. They were planted the same day. And when I removed one plant from these clods, you can also see that the rooting system was really different, and that root development was really much more extensive in the well-structured soil. Now, second portion of that presentation is about how cover cropping helps soil health more directly. And it helps in increasing soil organic matter content, but the cover cropping strategies are not all as good. There is a major difference between planting perennial crops that will have living roots continuously present in the soil versus, say, temporary cover crops that we plant, after harvesting the main crop or planting as an intercrop and so on, because the living roots are not there all the time. So that's the main difference explaining here that we get much more carbon accumulation or organic matter accumulation in soils where we have continuously living root systems. And the main reason is that perennial crops have a different strategy to allocate their photosynthetates within their tissues. The perennial crops really, they root 30 to 50% of the photosynthetates. They root them to the root system because that's the portion of the plant that will survive to winter. Whereas in annual crops, there is only 20 to 30% of photosynthesis that's allocated to the root system, because the very important thing for the plant is to perpetuate through its seeds. So most photosynthesis is allocated to the grain. But there is also an important point here to know that, these are different perennial forage crops that we can use to grow, say, in Eastern Canada more specifically. You can see that depending on species, the root development is way different. So it's very important to consider, say, mixing crop species, to have a good root effect, say, throughout the soil profile. But we also see the same thing, for annual species that are used as cover crops, temporary cover crops. You see that depending on the species, there are very different ways of developing their roots there. So again, mixing species here can really be beneficial to help developing a good soil health and then structure throughout the soil profile. This is a good example here of a farmer that I'm following, that I've been following for a few years now, where that farmer uses a mixture of different annual crops to establish a temporary cover cropping post-harvest of winter wheat. So in the region where he is located, we harvest wheat, say, in the third week of July or so we can establish a new cover crop in early August. So he's been doing this for about 10 years now. And so he plants early August that mixture of about 10 different cover crop species. And 2 months later, you can see the huge cover crop that develops. But what's really interesting is that if we dig in the soil, we can see that some of the plants have already 2 months after planting, seeding, they already have roots, as deep as 60 centimeters. So that means that the soil is really well structured, and there are many biopores through which the plant roots can develop, at depth quite rapidly. And we realized that on that farm, the soil bulk density down to 45 centimeters is always zero point 0.1 to zero point 0.2 units lower than the average farms, neighboring cash crop farms around. And it may seem just a small difference, but 0.1 to 0.2 in bulk density means a lot of much more porosity in the soil. Now, why are roots so interesting? I think it's really because of their capacity to, say, inject carbon or organic matter in the soil, especially at depth without mechanical tillage. I've surveyed a number of farms growing cover crops, temporary cover crops after harvest, say, in the province of Quebec. Under the Quebec Living Lab research. And I'm presenting here an average of the 2024 records. So in general, the above ground biomass was quite variable at the time when we sampled it. So we generally sample in the days when we know there will be killing freeze. And the biomass, the aerial biomass, you can see, was quite variable from farm to farm, going from 0.2 to up to more than 8 tons of dry matter per hectare, with an average of 2.4 tons per hectare. If we use the percentage, the efficiency percentage that I've presented at the beginning of the presentation, so it makes 0.2 to 8.4 times 12 to 23%, gives you a range of organic matter forming in the soil, going from as little as 24 up to close to 2 tons of organic matter per hectare. And if we take the average value, it gives you 288 to more than 550 kilograms organic matter per hectare. Now we've also measured the root biomass down to 45 centimeters and found that there was 1.4 up to 3 tons of dry matter per hectare present as roots for an average of a little bit less than 2 tons per hectare. So if we use the 45% efficiency coefficient, it gives you a range of 630 kilos to 1,300, more than 1,300 kilos of organic matter per hectare. And if we take the average value, gives you a value of 855 kilos. So for a little bit less biomass on average with the roots, because it's more efficient in forming soil organic matter, we end up with more, on average, with more organic matter that will be formed with the root biomass than the above ground biomass in the end. So that also makes me concluding that first we realize that roots develop very rapidly at the beginning of the growing period for these plants, and also that we have to consider that root exudates and root turnover, they represent a lot of organic matter that's not taken into account, that we can't take into account when we measure root biomass. And in general, in the scientific literature, it's considered that we can estimate that it is about 50% of root biomass. So that means that to the 150 kilos of organic matter, we should also add more than 400 kilos for a total of close to 1.3 tons of organic matter per hectare. Now, last point I would like to make is about the relationship between soil health, what we've seen before, and nitrogen management. Is there a blind spot? When we consider nitrogen uptake efficiency, okay, from mineral fertilizers, on average, we know that for cereals, and that includes corn, it's around 33%. So that means that about, on average, a third of the mineral fertilizer will be actually taken up by the crop on the year of fertilization, and it rarely exceeds 50%. With organic fertilizers, it's even less because the nitrogen is not all available in the first year with these organic fertilizers as compared to the mineral ones. So there's plenty of room for improvement. And there are different ways we know work that help improve the nitrogen uptake efficiency. And in general, most of the practices that we try to include have two main points, I would say. One is to avoid unnecessary and prolonged accumulation of nitrates in the soil. It will help reducing greenhouse gas emissions and nitrate leaching, more specifically, and also avoid the presence of ammonium and H4 at the soil surface. And that is very important when we use either urea or animal manure, more specifically. So doing this reduces ammonia volatilization. So these two points just help to keep the nitrogen in the soil. Fractionating the application rate is also very efficient in general because it helps adjusting the actual capacity of the crop to rapidly take up the applied nitrogen. Also, applying directly to growing plants is a good way to improve nitrogen uptake efficiency. So applying to living prairies or to growing fall cover crops, especially non-legume species, is a good approach. But we also have to adjust application rates based on the actual soil and supply capacity, and we'll see later on what it's all about. But we also have to make sure that the plant can efficiently take up the applied nitrogen. Okay, so is the plant ready for this? And one of the concepts that we regularly hear about to improve nitrogen uptake efficiency is the 4 R's nutrients to a chip concept that says that we have to apply the right nutrient source at the right rate, right time, and the right place to produce the economic, social, and environmental outcomes desired by all stakeholders. However, my question then is nitrogen efficiency just a matter of managing application? And I think it's not. Okay. Because, to any terrestrial or a living organism, there are 3 basic requirements, okay? First, nutrients, so we've just talked about it, but also water and oxygen. If we need the 3, so if we're missing either one, we'll die. But the interesting thing is that we'll die if we're missing oxygen just for a few minutes. We'll die if we miss water for a few days, and we'll die if we miss nutrients for a few weeks or even a few months. So it's funny to see that we generally focus on nutrient availability in the first place, while the water and oxygen availability seems to be taken for granted. But good nutrient uptake efficiency by the plant depends on good soil air circulation. And what we have to know is that above ground plant respiration does not provide any oxygen to the root system, because the root system have an really respire directly from oxygen that's diffused from the atmosphere to the soil, through to the soil. So uh, soil oxygen is really crucial to good root development. So if we take back our three basic requirements, we then see that oxygen really is very important. And so that maybe the 4R approach should be redefined as a 5R approach, where the right soil conditions are considered at the same time as the right source, rate, time, and place. A very good example here I'm presenting. That's a photo of the soil profile of the field where I have my long-term plot experiment. That's a very fertile soil. And this soil is a sandy, silty loam. You can see three well-defined horizons. So the top A horizon is very rich in organic matter, well-structured. The B horizon, you see the reddish color, indicating that there is iron there, but that it is, there is oxygen, so the iron is taking a reddish color, and the C horizon is, the decomposing rocks there. So this soil is very fertile, but I had a colleague about 100 meters away from that site that was trying to grow plants in a nearby field with the exact same soil series. So that's the same soil type, but the chemical analysis were very good in that soil, but everything was dying off, in wet periods. So you can see the photograph on the upper right-hand side. As soon as there was a light rain, we could see that the water was staying at the soil surface. So we decided to take a soil profile and see what was going on. And you can see by the color that it's way different. The A and B horizon more specifically are really have really a different color. They were saturated with water, and the base of the B horizon here that was still reddish was just dry. So we had a heavily compacted soil zone here, just above the reddish zone. So it prevented water to go deeper in the soil profile. So all the water was staying above that compacted layer. And the topsoil was also pulverized. So the soil macroaggregates were pulverized. And here you can see the photograph showing bluish and greenish colors. And this is again iron, but iron takes these color when in the absence of oxygen. So the soil was really badly structured, and there was not enough oxygen for the roots, plant roots, to grow. So they were just dying. So that shows you really an extreme situation, but that it shows very, very well what happens when the soil structure is not taken into account, and that oxygen is not able to circulate through the soil profile. Now back to the nitrogen uptake. What we know is that soil is the main source of N for crops, not fertilizer. And we did several experiments over the years to show that. And I developed a way to distinguish the origin of plant N that's present in the harvest for non-legume grain crops. And we showed that, whatever the crop, there is about 10 up to maximum 50% of the nitrogen present in the harvest that's coming from the fertilization, whereas at least 50% up to 90% comes from the soil reserve. And maybe this is not that surprising considering that there is 4 to 10 tons of nitrogen in the top 30 centimeters of soil already. So about an order of magnitude greater than what we generally add on a yearly basis with fertilizers. And generally, this is a gross estimation, but we can estimate that 1 to 3% of the soil and reserve is released to the plants each year. So if you calculate 4 to 10 tons times 1 to 3%, it gives you a range of 40 up to 300 kilos of N per hectare that's released each year. But the question then is, are your roots ready for this? Is root development and health status adequate? And we'll see that that's very important because we more and more try to rely on cover crops, prairies, and so on to provide nitrogen to the following cash crops or grain crops, say. And here I'm showing the results of one experiment using temporary cover crops that we've planted after spring barley harvest. So it was early September for that experiment, and then I'm showing the result more specifically for forage radish and oats. So the crops were planted right after barley harvest, and we fertilized with 50 kilos of available nitrogen per hectare, either as mineral fertilizer or hog manure, liquid hog manure. And at the end of the growing period, just before the killing frost, we removed the plant biomass and looked at what was captured. And we really were pleased with results where more than 50 and up to close to 98% of the applied N was captured, within the plant biomass. So we thought, hey, okay, it's going to be great next year with the following crop. That was spring wheat. And at wheat harvest, we rather were displeased with results where only less than 10% of the initially applied N was actually recovered within the harvest with grain. So we were kind of disappointed, but we also had the mean to get back to the soil profile and look at what was left in the soil reserve a year after application. And then we were happy to see that there was still 1 to 2/3 of the initially applied N that was present in the soil reserve. So that led us to conclude that this nitrogen wasn't lost to the environment, but would be gradually released through a legacy effect over the next years. So that led us to conclude that when we grow cover crops, we feed the soil so that eventually it can feed our crops, and that the soil and supply through legacy effect will spread beyond the very next year, so may spread over a full rotation. And again, we have then to make sure that the soil conditions and root health are good when nitrogen from the soil reserve is actually released. Now, we also had an experiment with prairies and saw that there is actually a synergy between prairies and animal manure We have a long-term experiment. At that time, when we sampled the soil, there was already 21 years of history, where we would apply either dairy manure or mineral fertilizers. And after 21 years of different crop rotation, we sampled the soil and looked at the amount of carbon that was present in the soil that had been previously applied, over 21 years with manure. So in a continuous annual crop rotation, we measured that actually there was as much carbon lost as CO2 as there was carbon added with the manure, with the yearly application of manure that was retained in the soil. So it was even. But with the rotation where annual crops were rotated with a 3-year prairie over 5 years rotation, there was 36% of manure derived that was actually retained in the soil. So that was lost as CO2. So that's very interesting. And we then looked at the nitrogen stocks in the soils and realized that actually there was much more nitrogen stored in the soil where a prairie was included in the rotation as compared to the annual crop rotation. So we looked at the soil and supply capacity of soils with and without prairie in a rotation. And so this is a different experiment than the one that I've just presented, but you'll see it's related. So we had 3 different crop systems. Our reference system was a very conventional one. So with only annual crops in rotation, there was a 6-year rotation with mineral fertilizer and soil plowing each fall. Along that field, there was another field where we had the same annual rotation, but a portion of the mineral fertilizer was replaced with the equivalent of 20 tons per hectare of dairy manure on a yearly basis. And the third system included a 3-year prairie rotation over the 6-year rotation. And we also had the same amount of dairy manure applied each year. So after 25 years of these 3 systems, we looked at the soil and reserve and measured that there was, as compared to the reference treatment, replacing a portion of mineral fertilizer with some dairy manure ended up with the increase of the soil and reserve by 20%. And if there was also a prairie included in the rotation, there was 50% more N present in that soil after 25 years. So on the 25th year, we were at the end of the prairie phase of the rotation. So we destroyed the prairie, and on the 26th year, we had corn everywhere. So we could compare, the amount of soil N that was collected by corn, that was present in corn at harvest. And we really were, some problems with the mouse. So we measured that there was a disproportionate amount of nitrogen supplied by the soil and collected by corn as a function of the increase in the soil and reserve. So that for a 20% increase in the soil and reserve, we had twice the amount of soil and present in corn as compared to the reference treatment, and with 50% more nitrogen in the soil reserve, there was 4 times more soil and present in the harvested corn. So you see, we were exceeding 200 kilos of soil and in the corn per hectare. So that shows that the soil, especially when there are prairies in the crop rotation, can supply a lot of nitrogen. But again, the following crops that could benefit from that must have a very good root development. So, in summary, the improvement and sustainability of soil health really depend on regular inputs of fresh organic matter, and the source of organic matter matters. Of course, knowing now that roots are very disseminate, that cover crops, the above ground portion are relatively good also and comparable to animal manure, and that mature crop residues are less efficient at forming new soil organic matter. Covering the soil with perennial species maximizes the benefits for soil health. Temporary cover crops help getting closer to this scenario, and mixing crop species, especially species with different rooting patterns, will help improving and sustaining good soil structure for the whole soil profile. Living roots foster soil microbial activity. We'll see. We've seen that, especially in the rhizosphere area, thereby fostering formation of macro aggregates and stable organic matter in the soil. Cover crops are also essential to improve nitrogen uptake efficiency. They can rapidly and efficiently take up post-harvest residual nitrogen or fall-applied nitrogen, protecting against winter-spring losses. They create and maintain biopores at depth, which help, deep root development, and they also increase the soil and reserve and its capacity to supply and to crops. So let's use it as much as we can, but then we have to remind that we have to make sure that our roots are ready, that the soil conditions and the root development is adequate. So that ends the presentation. And if you have questions, I'll be glad to answer these. Thank you.
Perfect. Thank you, Martin. Wow. Don't have any in the chat yet, but I have some because I always have questions. I'm a curious mind, you could say. So in the prairie system, and I'll watch the Q&A, so if anyone has questions, please put them in there now. Um, it's a common practice on the prairies here after
Mm-hmm.
bale grazing to be able to harrow the bale grazing site afterwards to distribute the residue feed and manure that's left over. Can you talk about how that would affect the mycorrhizal fungi or any type of community that would be affected by harrowing?
Yes, well, first, I would like to maybe know what's the tillage depth, roughly an inch, 2 inches, three, or
It
but because
normally,
that, yeah,
yeah, it normally doesn't till the soil very much at all. It just rakes all those
okay,
materials.
okay. So then the impact on the fungi should be really minimized because they grow in the soil. They of course can be at the soil surface, but if you distribute by harrowing, you distribute more evenly the leftover forage and manure. I think it's just a good thing because you will evenly distribute the resource for the fungi, but also bacteria and everything that's living in the soil. So I think it's a good way to do things, in my opinion.
Perfect. We do have some few questions in the chat
Hmm.
here. So the first one is, what is one small change a farmer could make this season that would have a meaningful impact on soil health over time?
Well, I would say that if you don't know too much about how your soil is structured, and more especially at depth, digging a few holes in your fields could be really informative to know first, do I have a structure problem or is it already well structured? So to my opinion, would just help in making good decisions afterwards, because you will see if you really have to change things, because if your soil is already well structured, it's probably because you're already using good practices. So you could then uh, look for maybe a new practices that will, uh, you know, probably help building up soil organic matter in the soil. But if the structure is not as good, maybe you may target practices, that will just first help in structuring, well structuring the soil. Mm, Yeah, so I hope it answers the question.
Perfect. I do have a follow-up to that of what type of soil at-home testing or apps could farmers use to better understand their soil structure? Like the Slake's app, you can do aggregate stability, or there are other ones
Yes,
that you recommend.
yes. Mhm. Well, yeah, measuring the aggregation, using either slates or another way to measure it is a good option. I would say it's very important to make that measurement, say, in the top 20 to 30 centimeters maximum. The other way to maybe assess the porosity at depth would be to, use soil cores that you can sample in, using a metal cylinder or something like that that you push into the soil and then remove them and just uh, turn them upside down and have a visual look at if you can see, biopores, because in general, most biopores are, you can see them easily. So if you can say, if you hardly see any, you could probably, that this would indicate that you could probably find ways to, increase the number of biopores. But if you say, evaluate that you have maybe 50 or more biopores per meter square, say, area, you're really in a good situation, I would say.
Perfect. Um, Another question here from Allison. What are your thoughts on using compost and how can it influence soil health?
Well, I think that compost is a good way, to improve soil health and soil structure as well. Um, I think it's a good source, and it's probably comparable to animal manure and cover crops as well. But it kind of depends on what were the initial materials. So if it's really rich, say in woody residues or things like that, it will probably uh, decompose more slowly, but at the same time, it should leave less organic matter present in the soil as compared to a compost that would be made of more biodegradable weedy plants, or you know uh, if there's a significant portion in the compost of animal manure and so on, would probably be decompose more rapidly, but at the same time leave more soil organic matter in the soil. But in general, compost are a good source of organic matter.
Perfect. Next one is a question on how farmers can better learn from each other when it comes to soil health practices that are working locally.
Yeah, I think it's very important that farmers, maybe local farmers, you know, meet all together on a regular basis. Um, we have here in the province of Quebec what we call the producers cohorts, and these are groups of producers between 12 to 15 producers all together on a specific topic. That they meet about. say 4 times a year, inviting either producers that are, really advanced in using good practices to present them their results and discuss about how it can be implemented, in their specific situations and so on. I'm often presenting stuff that like I've just presented to you today, to farmers cohorts. So it brings, ideas, information, about what happens in the soil, and then it helps the farmers while they're the court is meeting, all together to exchange on the way they can implement specifically things, in their specific cases.
Perfect. And to join our dairy hubs. I gotta put a plug in there. Um, okay, we have three questions that are on mainly cover crops. So, in a compact clay soil, is there a cover crop species that you would recommend?
But uh, depending on the extent of compaction, if the soil is really compacted everywhere, and that the compacted layer is thick, using cover crops, whatever the species, may not be sufficient. You may have to make deep tillage operation first to break down that compacted layer, but afterwards, the best way to preserve, all the cracks that were created by the mechanical tillage. So if you want to preserve this, you have to then plant a mixture of crop species with some deep rooted species. So the roots will go through the cracks and then create biopores, before the cracks close down. So yeah, that would be the best way. That's the way we did it, with the example of the soil profile that was totally degraded, uh, that I've shown in the presentation. So there was a deep tillage operation followed by a 3-year prairie of different species, including alfalfa was our deep-rooted species. But depending on the area where you are, there might be other ones. Tall fescue is very good also for deep rooting. Yeah, so that's the way I would proceed.
What about things like the Tilish radish or parsnip or anything like that?
Well, actually, what we realize is that tillage radish, well, the opinion that we have of tillage radish is maybe, you know, not close to reality, because when tillage radish hits a compacted layer, it will start pulling, out of the soil. So it can't get through the compacted zone.
Okay, that makes sense. Yeah, when you see them start
Yeah,
growing out of the soil
yeah.
instead. Good. Perfect. Next one. In sandy soils with low soil organic matter and low aggregate stability, is there a preferred cover crop to help build soil organic matter over time?
Yeah. Well, uh, in these soils, I would say that including a prairie phase in the rotation is probably the best thing you can do. But if you have annual crops, maybe using practices that help you covering the soil as much as possible and as long as possible over time with living plants. Uh, is the way to proceed to increase soil organic matter in sandy soils. That's for sure. And again, well, I would say that in sandy soils, probably that plants that have a very dense root systems in the topsoil will really help in aggregating the soil and stabilizing, against water or wind erosion. Because sandy soils will some sandy soils can form aggregates, but they're really fragile, really they're not very stable all the time.
What would be some of those species that would have that really fibrous root system for it?
Well, there are perennial crops, of course. Most grasses are very good, in stabilizing topsoil, and cereals are really good as well. Their root system develops pretty fast. There might be other species such as sunflower and then clovers, well, red clover, more specifically. These are all very good species to grow.
Okay, perfect. Then we have a similar one to about our complex
Yeah.
compact clay soils. Just
So
that
again,
severe
yeah,
compaction.
yeah. So again, if the first thing would be to dig and look at the compacted layer. Okay, can you find it anywhere you dig? And what's the cause? It is. Is it because of mechanical equipment passing over, repeatedly, or is it a natural compaction phenomenon? So then you can decide if you first have to break down that compacted layer using mechanical tillage, deep mechanical tillage, or if you could directly use some deep-rooted plants, such as alfalfa is very, very good in general to develop deep roots and form uh, large macropores at depth. Um, for annual crops, I don't know if there are species that are as good as alfalfa and tall fescue as well. So yeah, I would go probably. I think that there should be some mechanical tillage first, and then planting, say for 2 to 3 years, a mixture of tall fescue and alfalfa would probably really help to develop a good macro porosity density, at depth.
Perfect. We still do have a few minutes, so if anyone has any last burning questions they want, uh, type that in the chat. I did have one that we'll ask, and if there's one more afterwards, then great. If not, I do have another one in my list too. So as your background with soil, can you discuss the role of, I know you did lots of manure research in dairy. How would actually having animals really well managed on a perennial pasture system differ to spreading manure? Did you do any projects on looking at the soil aspects between those two practices?
Well, of course, when you're spreading manure, you have more control on, how evenly it's distributed across the surface. But I think that if the animals are well managed and displaced regularly over different paddocks or so on, the distribution won't be too bad neither. So it should be okay. But of course, you have a little less control on where where the feces and urine are landing when it's a pasture. So that's the only difference I would see. I think but in another way, I've heard that when the grass is cut, mechanically cut, it doesn't regenerate as well as when it's grazed. So apparently there's also a synergy between the animal and the plants there. So if it regenerates more quickly when it's grazed, probably I would say that the root system is also probably functioning better when the plants in the prairie are grazed rather than mechanically cut and harvested.
Perfect. Thank you. We did just have one question come in for the chat. Do any cover crops or combinations provide more concentrated improvements to nutritional density of the crop that follows?
Oh, that's a very good question. I don't have a simple answer to that. What I do know is that when you terminate the prairie, the following crop, well, in eastern Canada, it's often corn that's cropped following after terminating a prairie. And in general, we made nitrogen response tests in over more than 100 farms across the province of Quebec, and in more than 95%, we had no response to nitrogen and no response to phosphorus either. So I think, and these prairies generally were a mixture, of at least one grass and alfalfa, which is very popular in our region as a prairie species. So, say Timothy alfalfa or Timothy tall fescue alfalfa, and in general, the year following the prairie phase is a year when we generally would need no nitrogen at all and no phosphorus either for growing corn or canola.
Wow,
Mm,
that saves a lot in fertilizer costs for sure.
yeah.
Okay, I'm just going. We have one last question, and it's you'll answer it while I share my screen. Uh Probably it's a good one. So, what is the best way to terminate a prairie? So that would be a perennial system for soil structure wise.
Yeah, very good question. And maybe kind of tricky because you can decide not to till the soil to protect the structure, but we've discovered that the prairie will if you don't till the soil and plant, say, in the living prairie the next spring, you may have problems with nitrogen availability because there's a lot of carbons accumulated that will, cause a temporary uh, nitrogen immobilization. So it might be a problem. So um, you may decide, to till the soil, but then I would say I think it's probably preferable in terms of seeding a following crop to till the soil. But as much as possible, tillage should be, as shallow as possible. So maybe say 2 inches, not 5 or 6 inches deep, uh, just to kind of scrape the topsoil, and kill the living plants there, and then plant the next crop, something like that, so that the soil structure, below that depth, the soil structure is preserved, and the fungi that are there and that are not, perturbed, say, by the topsoil tillage will, regenerate quite fast and repopulate the topsoil quite rapidly.
Perfect. Thank you. Yeah, I had to ask that last question. It was too good. So thank you again, Martin, for doing this webinar with us. Very beneficial. I got a ton of notes here, and we do as a team. Thank you for all the participants for taking time out of your day and all of the staff that helped me put on the webinar. We could not have done this without everyone. We do have, as you leave the webinar, it will automatically pop up in another browser as a survey for the webinar. So if you guys can take 2 or 3 minutes to do that, that would be really beneficial. We also do have this QR code in the corner that will let you really find out what we're doing, and all of our other links to find out and connect with us are there. If you're interested in any Manitoba programs, my email's up there. Quebec programs for Regeneration Canada, Juliet's email, and any questions, Martin has graciously gave us his email. So if you have questions specifically for him, you can email him and go ahead for that. Otherwise, thank you everyone and have a great rest of your day.
Everyone.
Thank you.